My name is Natalia Keverle. I work for Ontotex and have some affiliation with Zaporozhye National University. I'm now the head of chair of the section. We will have three presenters, three groups of Ukrainian scientists, and first we will have to invite to talk scientists from National Academy of Sciences of Ukraine, Anatoly Doroshenko, Ilya Chour, and Olena Yatsenko. As far as I understand, Olena Yatsenko will present. Please share your screen and let's start.
Oh, yes. The presentation is devoted to the review of the results of applying algebra algorithmic tools for automated design of programs that use narrow evolutionary methods. Artificial neural networks are used in various areas of computer intelligence applications. Neural evolution is a family of machine learning techniques that use evolutionary algorithms to automate the creation of neural networks and facilitate the solving of complex tasks such as games, robotics, and modern natural processes. One of the most well-known implementations of such algorithms is narrow evolution of augmented topologies, or NEAT. In this presentation, the facilities for automated design and generation of programs that use narrow evolutionary algorithms are proposed. The tools apply high-level specifications of programs based on Glushkov's systems of algorithmic algebras, SAA. NEAT is a genetic algorithm for finding artificial neural networks through evolution. It simultaneously changes the topology and the value of the weights of the connections of the neural network. In the beginning, we have a very simple topology consisting only of input and output nodes, as well as optional hidden layer of nodes. A genetic algorithm, through crossing and mutation, automatically produces other topologies, which are evaluated based on the fitness function, from which the best ones are selected to continue the generation of populations. The quality can be monitored by observing a plot of the fitness function versus the number of populations generated. This here shows the programming automation tools which are being developed. In particular, it's the Integrated Software Design and Synthesis Toolkit, IDS. The toolkit is based on high-level schemes of programs represented in the systems of algorithmic algebras. It's intended for generating programs for parallel platforms, including multi-core processors and clusters. The main components of the toolkit are the designer of algorithmic schemes and the generator of programs based on them. The design process uses a database with descriptions of algorithmic constructs, which contains implementation templates with programming languages such as C, Java, and Python. This table shows the main constructs of algorithmic algebras used in the process of designing algorithm schemes. Namely, its composition, serial execution of operators. Second is branching, and then a loop. They are represented in algebraic and natural linguistic forms. Adjusting the toolkit for designing Narrow evolutionary algorithms consist in adding the descriptions of the corresponding basic operators and predicates to the database of the IDS toolkit. The table shows examples of uh, algorithmic constructions for narrow evolutionary tasks and templates for their software implementations. These are basic operators for working with populations, configurations, genomes, and fitness function. As an illustration, consider the use of the IDS toolkit for well-known single pole balancing problem. In this experiment, the NEAT algorithm is used to implement a controller that regulates a physical device. The SRR facilities and the IDS toolkit are used to implement a card device simulator and a narrow evolution-based control algorithm to stabilize the inverted pendulum over a given time interval. The initial configuration of the neural network of the controller is represented in the figure on the left. It includes 5 input nodes for horizontal position of the card and its velocity, for vertical angle of the pole and its angular velocity, and additional input for bias. Also, there is output node, uh, which is a binary node that outputs a control signal, null or 1. On the slide, the scheme of the function performing the experiment is presented. It starts by loading hyperparameters from a configuration file and generates the initial population. The evolution process is performed for the specified number of generations. After the best genome has been found during the evolutionary process, the operation is made to see if it meets the fitness threshold criteria, which is set in the configuration file. The program returns the genome with the formal best match. Based on the designed SR schemes, the IDS toolkit generates a program in the Python language using the methods of the new Python library. The figure shows a graph of the optimal single pole balancing controller found by the NEAT algorithm. The best genome, which is the winner of the evolution, encodes the neural network phenotype consisting of one output and 3 connections from input nodes. Unlike the initial configuration of the neural network, the velocity of the card is not taken into account. This graph shows the changes in fitness values over generations of the evolution. The average fitness of the population in all generations was low, but from the beginning there was a beneficial mutation that gave rise to a certain line of organisms. The gifted individuals from the line were able not only to preserve their useful traits, but also to improve them, which ultimately led to the emergence of the evolutionary winner. The conclusion. The adjustment of the previously developed algebra algorithm toolkit towards the automated design and generation of programs using neural evolutionary algorithms was proposed. The toolkit is based on the construction of high-level specifications of algorithms represented in systems of algorithmic algebras and generation of corresponding programs based on implementation templates in the target programming language. The approach was illustrated by the example of designing the program for the single pole balancing problem, which uses the narrow evolution algorithm of the NEAT Python library. So I finished my presentation, and thank you for your attention.
Thank you. Do we have any questions? Raise your hands with clicking the mouse while you're thinking. Oh, please, Vadim.
Thank you very much for a very interesting presentation. Can you hear me well?
Yes.
Yes, it is.
Excellent. As far as Dictory is built on the focus which is in the conjunction between academia and industry, the question is, what are the possible prospects or perspectives to use your approach in industrial applications?
Yes, there is a possibility to use in the industry sector if we find such applications which are applicable for this method. But at present, we used for simple algorithms. This toolkit was used.
Okay, thank you very much.
Who wants to ask more? I would like to ask regarding the NEAT library. So the NEAT affects, as far as I understand, the NEAT affects the structure and parameters of topology. What structures did you test it? What I see, it was a simple 2 layers and one hidden node, which then was removed. So what are the topologies you have tested already?
I only tested this particular configuration because the algorithm was actually developed by other person, so I didn't test other configurations.
So you applied the combination of Glushkov's algebra and narrow NEAT library to solve balancing pole, right?
Yes.
How do you feel about scaling this solution, this technology to other topologies, for example, for convolutional neural networks or other interesting topologies used in contemporary decision makings?
Yes, it will be a good application of this tool.
What part, if you go at slides, go to your slides, and if you show the set of possible operations, how do you feel? What operations would be added, or what operations would be like duplicated for other topologies? So I feel that there are some like predefined and should be operations, and what part of operations you provide is like removable or replaceable with other. Yes, exactly this slide.
This kind of operations, I think, has to be replaced with new operations. But we will have to investigate the new subject domain, I think, for adjusting the toolkit for generation of such programs that you mentioned.
Yes, so it looks like this research is like a proof of concept, right?
Yes.
And it shows, do you have any parameters of time or memory used? You didn't publish it in the paper, but maybe you remember or just have it easily to show.
No, I didn't record any time information.
Yes, please. Thank you. Vadim, please.
Thank you. I'm looking at the slide, number 7, and I do wonder what. No, number 7. The previous
Number
one.
7.
The classes of operations. Number 7. Yeah. I look at the at the bottom row, which speaks about fitness. Could you please denote fitness in the context? What is fitness?
It's fitness as function value.
How does it look like? What is the meaning of this function?
Okay, I have to look up the implementation of this function to answer this question. Actually,
How is this fitness evaluated? Did you evaluate fitness in your experiments?
yes. One moment.
Okay, thank you. Perhaps somebody has
Mhm.
some questions.
I guess
I
the
know
most.
I
Please,
know
Olena.
that a population of 150 individual organisms was defined in the configuration file, and a fitness function threshold was set to 1. That's all I know.
So it's really, it looks like a proof of concept task, and I see that it opens up like a very interesting set of works in presenting different topologies in the IDS toolkit, and so you will be able to model or to optimize existing networks already known for the particular task. So it will be interesting to see how do you feel about the future? What is the future research?
We plan to research other need libraries and other subject domains for applying the developed tools.
Do you have any particular practical tasks in mind? Not only one pole balancing task.
Probably from other subject domains. Probably something connected with the problem of electricity and energy and infrastructure problems.
I see. So it might be possible to model the topology of providers of electricity. Well, it's very interesting start. It's very interesting paper as a start, and we would like to see the like a future efforts there in the field. Do you or anybody else here present? Do we have questions to Olena, to probably to other authors?
Oh,
Seems no.
no.
Okay. Thank you very much. Thank you very much.
Thank you.
Yes, is it possible you to stop the presentation by yourself? Oh, thank you. Vadim, can we continue with the second presentation?
You are the boss.
Yes. Are you ready? Are you ready? Our second presenter is a group of scientists from Kharkiv Karesin National University. Alexander Denego, Vladimir Donets, and Grigory Zholtkevich. And they will report on randomization of reduction strategies for typeless lambda calculus. Who will be presenting, please?
Alexander.
Shall we present?
Yeah,
Alexander,
hello.
okay.
Yeah, I will
Thank
be
you.
presenting. I will share my screen.
Yes.
Yeah, can you see it?
Yes.
Uh,
But sorry, it looks like it's somewhere shifted to the right side. Is it possible to? Oh,
let's
that's better. That's better. Mhm.
maybe it's only first slide. Yeah, I think it's
Okay.
only
It's only on the first slide. Okay.
okay. Okay, I can share with the PDF. Maybe it will be better. 1 second. And you can see it now.
Perfectly. Perfectly. Thank you.
So yeah, so good day, everyone. Today I wanted to talk about our paper optimizing reduction strategy in functional programming, and with a particular focus into lambda calculus and random strategy. So let's dive in. And first of all, I would like to say about problem statement, and basically. Today, we may recognize that in the rapidly evolving landscape, functional languages are gaining traction, and um, more people start to use them. And they look very proposing and a useful tool for software development. But on the other hand, they also pose a challenge, which is how to optimize the reduction strategy of the functional languages effectively. And this is basically the core concept and the core problem we will be talking about today. So, yeah, functional languages are gaining adoption, uh, and in the today world and modern software development. And basically, this is all thanks to concurrent and thanks to that they are perfectly suited for concurrent and parallel computing. And also, functional languages emphasize immutability and statelessness, which is really important in nowadays software development processes and tools. And on the plot, you can see the uh, gaining trajectory of functional languages, and basically this is the core idea, yeah. And such languages as Haskell and Erlang and Clojure, for example, they are gaining more and more people in their community. So let's talk a bit more about benefits of functional programming. And first of all, this is, I would like to mention declarative nature. So we focus on what rather than how during our programming process. And also it allows us to get easier debugging and testing. Uh, Also, functional languages give us such opportunity of using modularity and increased reliability for the software development, as well as scalability. So these are the main benefits, and they are very important for functional languages. But there is no such thing as free lunch, and functional languages, they also come with a set of problems that we will need to deal with. And first of all is I would like to mention steep learning curve, which makes functional programming languages challenging for newcomers. And because of that, we can have this first cluster of problem. Because of the steep learning curve, we are gaining limited, smaller community, first of all, of people using it, using functional languages. And because of that, we are getting limited frameworks and tools. So this is first cluster of problems that we almost cannot do anything with. And the second cluster of problems is potential performance issues, overheads in some tasks for the simpler tasks in imperative languages, and memory consumptions. And basically, we will focus on the second cluster with of optimizing of the performance of functional languages. And this will be the main focus of our research. So the reducible unit, or regex, or reducible expression, this is basically the core unit of lambda calculus, and it allows us to transform the complex term into a simpler one. And this is basically with executing of the redexes. This is exactly the process of computation of during lambda calculus program. And basically, here on these examples, you can see highlighted redexes of particular terms. And the idea is we will need to apply the left part to the right part and get a new term and new equation. And this process is called the reduction process, and this is the main mechanism of executing programs in functional languages. And yeah, as I mentioned, the goal is to transform complex expression into more basic and simpler. And we need to, it's crucial to understand that the efficiency of this process is really important for the overall performance, because each reduction step may take small or big time, and on the other hand, we will want to get as little of reduction steps as possible. So in our work, we'll focus on optimizing the number of these reductions or on the time of one reduction. And so as you can understand, in the case if we have several redexes in our term, we will need to decide which one to execute first and which is execute second. And for that, in functional programming languages, we have strategies, and we will focus on two main of them, which are call by name and call by value. And as call by name and call by value strategies, they evaluate values in different way, and we can say that call by name can be seen as the lazy evaluation of the redexes, because we only compute arguments of the function when we need it and try to pass function by name if it is possible. And in the call by value, on the opposite, we first of all compute arguments of each function, of each equation, and only then we compute the function itself. So this is the main difference of these languages. And as analogs for them, we can take a look at LO and the LE strategy. And basically, we can have a one-to-one, almost one-to-one relation between LO and call by name strategy and LE and call by value strategy. So as LO strategy, we first of all evaluate most left, most outer redex, and in LE, most left, most inner redex of the term. And if we will look at the term in the tree representation as a tree, then we can say that LO strategy evaluates first redex that we meet during breadth first search and OBFS, and in LE case it is depth first search or DFS. So we firstly evaluate redexes at the deepest redex as possible. So these are two main strategies we will focus during our work. And so yeah, it is very important to understand that different strategies gives us different outcomes, and strategy, the sequence of our reduction of redexes, of executing of redexes, depends on the strategy. That's why picking the right strategy is very, very important in our work, and as it influences number of steps directly, and the order of picking radixes. So yeah, different choices leads to different outcomes, and here we have example with one term, and if we will apply LO strategy to it, we will reduce it in one step, which is good. And in case of using LE strategy, we will get into infinity loop, and we will basically never reduce this term. So this is how different can be strategies and how different can be outcomes with different strategies. So if we have different strategies, we need to have a way to measure which one of them is better, and etc. And for the measuring of the strategy efficiency, we have two main ideas or possibilities, which are number of reduction steps and real processor time and resources. And number of reduction steps is a pretty direct and consistent measure, as it only depends on the term, and it is pretty easy to count it. However, it is very abstract, and we cannot say that 5 reduction terms of one term and 5 steps of another term will take same time in real life, and etc. And because it doesn't mirror real world efficiency. And for real processor time, is the opposite idea. It is very practical and comprehensive, as it considers overall system performance, and we can actually say that in real life this strategy with this term will take us such amount of time, and we can understand is it a lot of time or it's a small amount of time. But although it is very variable, because it depends on specific system setups, and time of reduction on one computer may not be same on the other, and etc. with different hardware and software. And during our work, we focused on number of steps for reduction, as it is theoretical, and I would say the most basic idea. So we started to work with this measure. And here you can take a look at this plot and how it was built. Basically, we took about 400 fixed terms, set of 400 terms, and we applied to them LE and LO strategy, and counted number of steps for LE strategy and LO strategy. And each point here represents one or more terms. If they're in one point, we will have like, here, for example, we have 11 terms, and they just have a similar amount of steps. So basically, this term shows us different interesting patterns, and the idea that people saw in life, and that this plot shows us, is that usually LO strategy reduces terms faster than LE strategy, and we can see that all these samples above this line are cases where LO strategy was faster than LE. But on the other hand, we have specific scenarios right here where LE strategy is faster than LO, and basically recognizing these scenarios is key to strategic optimization, and focus of our research in general would be to find these specific scenarios and say that in these scenarios we should not use LE strategy, we should not use LO strategy, we should use LE strategy. So basically, yeah, this is the main idea, and we can go next. So yeah, from the previous plot, you can understand, and from the previous information, you can understand that there is no one-fits-all strategy. So we don't have one universal optimal strategy, and for each term, we can, for specific term, we should pick specific the most optimal strategy. And from this example, we can see that LO strategy is faster than LE, but we can have exactly the opposite. For example, with omega term, we can have exactly the opposite situation where LE strategy will be much efficient than LO strategy. And because we have a term, and for a specific term we need to pick a specific strategy, we can see some analogs with reinforcement learning, because here we can say that term is a state and picking a random strategy is a action, or selecting the right action that we do. And because of these intuitions, we can see, look at this as a game. And so yeah, we have reinforcement learning using potential in the future because of these analogs. So the idea of our paper was introducing the random strategy, which is a blend of multiple foundational strategy. For example, we can imagine it's LO and LE strategy, which we discussed above. It gives us a hybrid strategy that combining element of basic ones, and it allows us to adapt and for specific set of terms with some proportions where LE strategy is more efficient than LO strategy, we can have this mixture of these strategies, which will allow us to be closely to optimal selection. And as an example of the benefits of random strategy, we can take a look at this plot and these two plots. And basically, we took one term, which is omega term for this scenario. And omega term, in our case, we were working with one parameter, which is called n. And the idea here is that left inner strategy, which is here, always have a linear dependency on this parameter of omega term for reduction steps. So LE strategy will take linear number of steps if you comparing to n, and for left outer strategy, which is same line as green, you can see here that they are very close, will take quadratic. And so of course we don't want to get these cases when we will have quadratic dependency or squared dependencies on the parameter of omega term. And we see here that our random strategies, inner random and outer random, they are always in between of these edge cases. So inner random is here, and outer random is not too much, but it is still below the left outer, so it performs better than left outer strategy. And it allows us not to get these edge cases. And for example, with other term, we can have totally the opposite situation, but still we will not get quadratic dependency. We will be somewhere in the middle. And basically, yeah, this is the core concept of the random strategy. And I think from my side, that's pretty much it. And thank you for your attention. And I'm open to any questions you have.
Thank you very much. It was very interesting and fruitful,
Thank you.
fruitful presentation. And if anyone has questions now, please ask. Please, Vadim.
Thank you very much for the presentation. It was really interesting. I do wonder, to have any practical results based on your observations and involving the implementation of this random strategy, to have a solver implemented?
Yes, so basically we have an environment which have two main functions for us is generating of the terms, and also in this environment we can put a term and a strategy, and it will tell us whole reduction process of this term and with this strategy, and will give us a number of steps, for example, time of each step and the state of the term on each step. And basically, this is the environment we are developing now, and most part of our research is around this environment. But in the practical, like real life practical, it would be great to have like some kind of compiler or something like this that is using our strategy.
Okay, thank you very much. And may I have one more question, please?
Sure.
Yes, please.
What are the practical applications of this functional languages based on lambda calculi? Do you plan to have, for example, industrial use cases for your solver or potential compiler in practice, in industry, in which domains?
Yeah, so basically, yeah, a compiler or a solver would be probably the final goal. And I cannot say about specific domain, but exactly, yeah, the compiler for Lambda for functional programming language, I think this is, yeah, the final goal. Yeah, this is, yeah, in terms of the practical usage.
Okay, thank you very much.
Thank you.
Can I have a question? What language do you use as a basis for experiment?
For experiments, we use Python language, and yeah, this environment is also built in Python.
In Python. And how do you... it's a question of probably... is it possible to have a complete set of possible views of terms? It might be a large set, but a fixed set.
Yeah.
So it will be easier just to analyze the strategies for reduction for each particular term, but from a fixed set, and you will know for sure how to optimize in each particular situation. Is it the case, or it is impossible to predict it, and the terms can be absolutely... So there is no system, no set.
No, yeah, we have a set, and basically here we generated about 400 in this case for this plot, about 400 of terms, and we have this fixed set, and we first of all evaluated every term with LO strategy and then with LE strategy. So basically for each term we already know which strategy is better, and the idea like of other possible research and is to find or to see these patterns of terms for which term one strategy is better and for which term another is better. And
because, yes, sorry, continue, please.
Yeah, so the idea is finding these patterns, but finding these patterns should be made on some set, for example, of specifically generated term or with, for example, code of real people on some programming languages. So we will have, so we should definitely have some patterns there. And if we have like all set of random terms possible, it will be like too much.
Okay, Vadim, please, then I continue.
Thank you very much. Just came to my mind that you might have taken a look to generative pre-trained transformers as an alternative for benchmarking against reinforcement learning architectures. Did you?
Yeah, so we tried to use transformers recently, and we took pre-trained transformer and we applied them, for example, for a term, for example, like here. And the problem was that each of these character were transformed into token, and when we passed it to transformer, it almost recognizes nothing because it was trained on the words, and it doesn't see any language patterns here. But we
Which version of GPT did you use?
no, it was not GPT, it was BERT.
And it doesn't see any patterns.
Okay.
Mhm.
Okay. It has to be fine-tuned, I believe. Thank you.
Now my last question, and we will go to the next presentation. The question is, when you say is that you generate terms. By generating, it means that you like predefine the possible set. You cannot guarantee that you know and you've seen all possible terms, because you generate, you provide a structure for generator. So it might be good, yes, indeed, to see the others, like real code, and to be able to extract the term structure from there, from real world applications.
Yeah, exactly. From real world, it will be. We are also thinking about it, and it will be like really useful. And but we are still thinking how to do it. Yeah. So yeah, we started with this generated data.
Okay. It seems that we will see in 2 years, we will see a practical application like your own reductor, and it will be nice to see it in practice, really, because it's like a problem for all the lambda calculus software tools. They are very, very, very slow and very, very inefficient. Okay. Thank you very much. If anyone has questions, please ask, or we turn to the third presentation. No questions? Okay, then thank you. Can you switch to another presentation, Vadim? Our last presenters is a joint work of Ukrainian Catholic University, Alexei Ignatenko, and Kyiv Academic University, Ruslan Prasov. They will report on combination of convolutional networks and Monte Carlo research for a game, for Sokoban, to avoid dead-end states. Please. Who will present?
Thank you. I will present. I'm here. So I will tell you about this approach that we used to solve this particular set of puzzles, and what we learn about this. Can you hear me? Yeah, it's good?
Perfectly.
Він включений.
Вам потрібно перейти на презентацію.
Okay.
Okay.
So I can either see presentation or everyone, but okay. So the plan I will tell you about Sokoban game and history of reinforcement learning usage for such rule-based environment. Then I will tell you about current solutions and then present what we actually the idea of approach we used, and what we get in result, and some conclusions and future work. So if we remember about history of reinforcement learning in rule-based environments, then obviously Arthur Samuel checkers, which were released in 1952, was the first example, and it was very interesting and prominent step in development, because it was a set of weighted equations that allow program to learn playing by itself and get to the level of strong amateur human player. So it was very unexpected at that moment. And after this, reinforcement learning got many different results, but the general idea was formulated by Arthur Samuel. We want to have a program which can learn by playing with other people, or maybe with other program, or with itself, and do small improvements in play. And because the program can do it well, almost without any constraints, we can actually get a high level of play. So probably the peak of the attention to this idea was due to DeepMind work, and when David Silver tried to apply this idea to Atari games, and then produce AlphaGo, which beat the human Go champion player, and later, and then they also applied this approach to shogi, probably the last board game which was too complicated for computational approach, and also for some general board game as well. So if I may to tell you that it was not so good for online strategic game as they planned, because we didn't hear a lot about their success in, for example, StarCraft. So what is the Sokoban? Sokoban is a Japanese puzzle, very old, and the idea is that we have here the environment, and in this environment we have patches of different types. We have walls, we have just empty floor patches, we have small targets, yellow crosses here, and we have boxes, and we have one worker, and this worker can walk in 4 direction and can push the boxes, can push boxes forward. Obviously we have some limitation behind. For example, if for human player, it's obvious that if you have box in the edge or near the wall, then you restrict your future options. So Sokoban has this ability that it looks very simple, but even if you take a look at left picture, how can you solve it in your mind? Can you push the box in to the yellow cross? Well, it's not really too complicated, but you need to understand that you need first go here. Sorry, I can't show you because it's it's fine, because this the pointer is not seen. It's fine. It's not the problem. It's a problem of laser. Laser is not shown on the board. Yeah, but you can imagine that this guy should go to the left and then push box 1 cell to the right, and then go to the up of the box and push box 2 cells down, and then go around and push box 1 cell right, and then push it up. So it's not straightforward. and also you need a lot of two types moves, pushes and go into the right position. And you see the right task, the right problem is even harder, because you have 3 boxes here and 3 places, and I bet that you probably will not solve this in your mind. So all this poses quite a challenging problem for the artificial intelligence and now machine learning techniques. So we have basically 2 main approaches. One is just ordinary artificial intelligence approach, where you have a search over a complicated tree with constraints, so you can apply different types of the search. And second, quite maybe recent approach is to use reinforcement learning to try to train the network, so network can understand how to push these boxes to the right direction. And we have here 2 big questions we need to address: is the irreversibility of some states, so network should understand that this state is like no way back from this state. And second is that you have these long sequences of action, and it's bad for reinforcement learning value function, because it's like gradient fading. So state of art, we can use this 2021 year paper, and you see that actually they didn't receive good result. If you have no hints about the problem, they have 55% or 60% of solved. If you have hints, and by hints they use some direct information what box should go to the what place and at what order, they increase significantly quality of solution, but it's still a quite challenging problem. Usually, yeah, they use this approach of expert iteration, where you have 2 main networks, two networks, and you have apprentice policy network and you have expert policy network, and they cooperate to get a best result. And usually usual architecture of this network is a convolutional, so you have a whole image of current state as an input, and as a output you have one value, and you have 4 probabilities for 4 moves. So these networks try to predict what move should this worker do in this situation. And if you have like different moves with the same values, then you can generate uniform distribution for them. And the second part is the Monte Carlo tree search, where you have search on the problem, but you don't search to the end. At some point you use your network to estimate the quality of state at this situation, so you just try to find better solution from this point, and then estimate the result. So this is a form of the equations they try to maximize when they use Monte Carlo tree search. Monte Carlo tree search with the estimation by actor-critic model. The second idea is the second idea is a curriculum learning, where you have many different actor-critic models, and they trained, and then due to some rules they update to the best of this curricula, and choose the best one. So they get this about 80% of quality. You have deterministic, stochastic, and actor-critic application. And this is the current state of art, depending of how many simulations you use per each move. So how long you see ahead for every move, and you see that deterministic extent and stochastic extent are usually are the best, and other two approaches are like not too good. So the ideas that right now are speculated in different, or maybe proposed in different papers, is to use different types of actor-critic models, use some heuristics, add some quantum machine learning, and also maybe transfer learning, and also learn by your sub-problem if you have one. So our idea is to use value network to estimate state instead of simulation in Monte Carlo research, because we try to use this approach where we try specifically learn train network to recognize these dead end states, and so if you have a real reinforcement learning problem, you have agent, environment, real state, and action, and our idea was to support this value function not by simulation but by direct labeling of dataset. So we at some point we try to combine reinforcement learning and usual supervised learning. Yeah, so our goal is to maximize expected return. So we have a reward for each state, and we have expectation over trajectory of agent. So we have two functions: state value function and action value function. State value function estimates the quality of state, and in Sokoban we actually have states that are winning, states that are losing, and states that are unclear, and the result is still unclear. And we need also to calculate for the pair of states the action which can translate from one state to other. It's fine. So this is an example of our Sokoban environment, which we try to how we will visualize our results. So as you see here, this left game is in deadlock because this box you can't put it from the edge, and the second one also the deadlock. So in our setup we use 6x6 game field, 2 boxes, and rewards were like this. Well, we somehow arbitrarily designed it so because from our experience it should work, and we put max number of steps per game is 250. So we have 3 kind of position. Deadlock, by starting position we mean that it can be any position that is unclear what result is, and the solution position. Our network architecture is also not very complex. It's a convolutional network and few layers and scalar output. The idea is that so this is an architecture, and the result in our architecture is to estimate the type of the state. So when we try, so what we did, we generate about 3,000 different games with states, and we label the states from solution state to losing state, and we try to predict the type of the state using this. So we have this mean square error, and before this it was a classification error. And when we add this value network to our Monte Carlo research system, we get this result. So we have the solution for random games about 40%, and here suddenly when we try to fine-tune this using the initial states, the result gets worse. Maybe we can work out how to understand this result, but it didn't work. So we tried other thing. We tried to add starting data states in data set, and this improved our quality a bit. So in our highest solved game percentage is like this. As you see, when you have about 100 rollout, so you try to solve on for every state, you try to solve 100 moves before using Monte Carlo tree search and estimate the quality of state you get. So if you have these three types of states and labeled data set as the base, you have 44%. So it's kind of a middle between the best result and like not very best results. So our idea is actually to add this data set with labeled states, and probably we can try also add separation between actions, because it's interesting idea that you have actions that push some boxes, and it can lead to irreversible position, and when you just go walk around the boxes, you never will get to irreversible position. You always can return. So you need to separate them, because obviously when you just go around, your value function should be different than when you push box, because pushing box, it's like very commitment move. So you need to be pretty sure that this is needed. And I think this can improve the result. And the second idea is to use bigger data set, and probably we should try to take bigger games, to bigger sized games, to understand is it approach is scalable for bigger games. So thank you. Yeah. Is it possible to click on this? I don't know. I don't know if it would work, but it's actually a link on the this image. Yeah, click on this. Just click. Yeah. Okay. Yeah. Okay. Maybe next time. Or maybe I will show you later, because it's embedded. Yeah, it's embedded. So if it's fine and you can see, yeah, click on the center. It's example of one game. So can you see it? No?
I can see only the starting board, but not the movement.
Okay. So
for me, it's like a static picture.
Yeah. We need to share. Just reshare this.
The link. Right.
In Meet. We need to share in Meet
It will
whole
be nice
screen.
in the chat. In a chat.
Can you copy link to the chat? Okay, maybe it's the simplest one, because it's allowed. Yeah, you can run it from anywhere. It's just a file on the Google Drive. So yes, this is example of a very simple game, but this reinforcement learning algorithm solve it without knowing anything about the Sokoban. So thank you. This is it. I'm ready to hear your questions.
Thank you very much. Do any one of you has a question? Probably, because when just can I have a question?
Maybe you can share this presentation if someone will have a question about this.
You. It should be Vadim.
Tade, as a boss, you may ask your questions immediately without asking.
Okay, thank you. No. When thank you very much. When you start your presentation, you told a lot of the roots of Sokoban game, and this was the cause of my first question. So when someone plans to go into game dev, he or she writes Sokoban or Tetris or somewhere and show this code like a homemade prepare file. So if you are going to have a benefits, you have to write Sokoban with like reinforcement learning or something else, or at least combining of the tasks. So you will have a lot of benefits in game dev. Are you planning to start a company?
Well,
or a startup or that?
I'm not planning, but actually it's one of the possible application, because the problem of creating of Sokoban levels is to create it interesting for people. Yes, so because sometimes when I play in Sokoban, because I like to play puzzles, and sometimes the level is so complicated that you feel a joy when you solve it, and sometimes it's not. So, and the question that actually bothers me is, what's the distinguishment? What's the difference between interesting level and not interesting one? Is it possible to train the network to generate interesting levels
Interesting
for
states.
people? Yeah.
I see. So it might have like a commercial. Let's see. I also like to see to hear the answer. So you playing like one player. How do you think if we add two players? Because I know you have a background in two players games. Is it possible to like speculate on the adding second player to the game of Sokoban and to recalculate the results?
Probably yes. I mean, sometimes level of Sokoban sometimes are so complicated that you can't solve it by one worker. So I can imagine the levels that is not possible to solve with one, but possible to solve with two, because sometimes they need to push boxes. Also, well, as usual, from point of usual game theory, it's difficult to, as I think, it's difficult to formulate a game which will be meaningful from the point of game theory. But you can always, if you have like two players, you always can try to solve the game for faster than other player. So, but it's not, obviously it's not a game. It's two games that try to do it faster, for example. So maybe it's possible, but I don't know. Is it the theory that can help with this game?
Second question: what if you apply a push and pull strategy?
Push and tool.
Push and pull. So you can push and you can pull the box.
Actually, it's one of our possible direction of future development, is to change a bit rules and try transfer learning for this game. Because if you allow to push and pull boxes, it's a quite different game. You can formulate a different level. Also, you can, for example, add some teleportation where you can just move the boxes or something different. So yeah, so it's possible to make some extensions and try to apply techniques of transfer learning. Is it possible to retrain model a bit faster?
Yeah, because push and pull just changes the state of the board, and you go from one state to another.
А може і в нас. З'єднання з мережею втрачено.
To 6 is 80 to 100, correct?
Yeah,
is it a fixed?
Yeah,
is it a fixed end?
Yeah, we had some network drop. But
how do you feel?
Now we can hear.
Oh, sorry. So how does the number of rollouts affect the performance?
well,
What is number?
number of rollouts is when you have I can give you example. When you have chess game, for example, you can look at 5 moves ahead, calculate 5 moves ahead, and understand what position will be, and then decide should I do this move or not do. So good chess players can calculate 10 and maybe 15 moves ahead, especially if there are special situations where you can do it very easily. So here it's the same. You have Monte Carlo tree search, which means that you do not perform full search. You try different searches in different directions with a length of rollout, and you estimate the position. So you can the hypothesis is that if you have good position, that nearby should be good position as well. So if you have a move that leads only to good positions, that probably it's a good move. And if you have moves that leads to bad positions, then probably you shouldn't take it. So rollout is the horizon, how far ahead we need to look at this tree. So obviously if you have a bigger size, then you need more computational power. So it's vice versa. And our experiments show that 80 actually is enough. So 100 improving from increasing from 80 to 100 is not improving the result. So 80 is enough.
Because I can imagine the plot of dependency of size of board and the number of rollouts, which will be the scale. What can be a curve?
It depends of the board. I mean, with positions and how many obstacles you have and so on.
This is just an idea. I would see how is it exponential growth or to feel this exponential, how the exponential appears here when you increase the size of board. It should exponentially grow.
As far as I remember, actually in this tree, the identical positions are not separated, so it grows pretty fast. So you need to, I think, separate them, because otherwise this tree can grow infinitely if you do not limit the rollout. They just make some cycles, for example.
I see. Yeah. Okay. Thank you very much. It was really interesting research. I also played Sakoban, so for me it was like, let's see. If anyone has questions, please ask. We have 10 minutes ahead, or we just can conclude the section. Okay, then
you may conclude
as a boss, yes. I would like to thank everybody presented and everybody attending this section. Thank you very much. Have a good rest, small rest, and we will stop the presentation now.
And before you escape, I'd like to thank Natalia for an impeccably conducted session. Thank you very much.
Thank you.
Thank you.
Okay, bye.